right, so here's number 15. A planet orbits a star. The distance, the distance from the star to the planet is 49.8 million kilometers. The time for the planet to orbit once is measured to be 0.2 years. Find the mass of this star. Okay, round one place past the decimal. So as soon as you hear that, right, as soon as you hear find the mass of the star, all right, you should be thinking, let's just go back to our equation sheet, right? So if you look at the equation sheet, which is right above where our sample problems are, there is the modified version of Kepler's third law. Anytime you're looking for mass, if the question asks about mass, this is the equation that you have to use, the modified version of Kepler's third law. The mass is in kilograms. The distance has to be in meters, and then the period has to be in seconds. All right, so we've got some conversions to do. Notice all of these. It always gives you what the proper units of everything has to be. All right. So here, let's go back to this problem, and let's work it out. Okay, so we're going to use the modified version of Kepler's third law. That's perfectly fine. But let's first work on converting the distance. All right, so the distance is 49.8 million means times 10 to the sixth kilometers. All right, so kilometers. Now we know it has to be in meters, so I've got to convert 1 kilometer. Right, so 1 kilometer is, of course, 1,000. Another way of writing 1,000, of course, is 10 to the third meters. All right, so the kilometer part cancels, and now 10 to the sixth times 10 to the third, you have the same base. So just as a reminder, I'll do it right here. 10 to the sixth times 10 to the third. You just add these, you add the exponents, right? If it's the same base, you add the exponents. So that becomes 10 to the ninth. All right, so it's the same number, 49.8 times 10 to the ninth. Now it's in meters. All right, so now we can do this. All right, what about the period? All right, so the period is in years, so it's 0.2 years, but we can convert that. In 1 year, there are 365.24 days. All right, so the years cancel, and in 1 day, there are 24 hours. In 1 hour, there are 60 minutes. Remember, we use MIN for minutes. We reserve lowercase m for meter. Right? So, and then of course there are 60 seconds in 1 minute. All right? So the minutes cancel, the hours cancel, the days cancel, the years cancel as well, and so we have all the numbers, and then we just have to plug in into the modified version of Kepler's third law, which is a challenge in and of itself. Anyhow, the answer that we should get when we do this one is 1.8 times 10 to the 30th kilograms. All right, so let's work on this. All right, so I'm gonna work on the period first here. So it's going to be 0.2 times 365.24 times 24 times 60 times 60 again, which is just 60 squared, equals. All right, so that's the number of seconds in 0.2 years. All right, it's a little more than 6 million seconds. All right, so I'm gonna just store that. Okay, so we're going to use that in a little bit. All right, so see if I hit this memory recall. It's in there. All right, so I've got the period, and let's and so the distance here is 4.9 times 10, 40. Sorry, 49.8 times 10 to the ninth. All right, so now I'm ready to use the modified version of Kepler's third law. I've got the period, I've got it in seconds, I've got the distance in meters, and I'm ready. And so I'm going to plug those things in. All right, so here we go. All right, so we have, there's the modified version of Kepler's third law. I wrote it all out. We just calculated the distance in meters. We've got to cube that, and then we multiply it by 4 pi squared, divide by big G, which is the universal gravitational constant. That's what this number is, and then we divide by the period in seconds squared. All right, and so we've got that number right here, which is in my calculator. If you remember, I just did that. All right. All right. So there's the. I already have that stored in my calculator. So, all right. So here we go. Let's do the numerator first. All right. So it's going to be 4 times pi squared. All right, and then times 49.8 times 10 to the ninth, so E times 10 to the ninth. Now I've got to cube that, all right, so they raise that to the third power. All right, and then I'm going to divide by big G. So I'm going to do 2 steps here. So what I'm about to do is, I just did the numerator, and I'm about to divide by big G. All right, so and then after that, we'll divide by the period squared. Remember, I stored the period in my in memory of my calculator. All right, so we're going to take that. And then here we can do this. We can do. You don't have to hit equals, but I'll just. All right. So anyhow, equals. All right, and then divided by 6.67 times 10 to the minus 11th, right? exp minus 11th, all right? And then once we get that, we divide that answer, right? So if I hit divided by again, now we're going to divide by the period squared. Remember, the period was in my I put that in memory in seconds, so dividing by that, but I've got to square it. All right, and so this will give us the answer. All right, and so notice, this is not giving us the answer in scientific notation, which is why I don't really like this calculator. But at least it shows up on these videos, so that's the only reason I use it. But at any rate, if I take this number that's in my calculator and divide it by 1 times 10 to the 30th, right, that'll get me 1.8. 1.8. The rest of these things. Okay, so divided by 1 times 10 to the 30th. I'm just proving to you that there were 30 digits in front of the decimal point. All right, so 1.8. So the next digit is a 3, so I don't round up. So it's 1.8 times 10 to the 30th. So that's the mass of this star. 1.8 times 10 to the 30th kilograms. All right, so that's actually almost the same mass as our star, which is 2 times 10 to the 30th. All right, let's do the next one. All right, this is number 16, the real exoplanet. So an exoplanet, of course, is a planet around a different star other than our sun. These are all stars, by the way, in our galaxy, the Milky Way. Those are the only exoplanets we can see right now, anyway. Anyhow, they give us the radius of it in kilometers, which we're going to have to change in both of these equations. R is the radius, has to be in meters, so we got to change that right away. All right, well, that's actually pretty easy to do. The mass has to be in kilograms, and it already is. The mass of this planet is 4.9 times 10 to the 25th. All right, this just gave you some information. All right, so find the escape velocity and from the surface and of the planet. Um, and the reason I say that is the way this equation is: r is the escape velocity. If you were to escape, that's the escape velocity from the surface. If you were to leave the planet from some height h, you just put r plus h. That's how the equation is altered. All right, so let's just change. I'm going to change it up here. So let's change r to meters, right? So that's actually, if you know that a kilometer is 1,000 meters, it's just 16980. And see, if I just you know just multiply it by 1,000, it would be 800, right? It would just be 800 meters. Or you could write it like this. It's exactly the same. 16980.8 times 10 to the third. They're both meters, right? Either one. You put this number in your calculator, it's indistinguishable from this number. It means the same thing. All right. Anyhow, so we're going to put those numbers in here, and here we go. All right. So I've written all the numbers that go into this equation. The only thing we really had to change, of course, was the radius had to be in meters, which I did up here. You just multiply the number that was given to us by 1,000 to change it from kilometers to meters. All right, so anyhow, let's plug these numbers in. And of course, these are the two answers that we should get. 19.6. So this one, at the end, after you're done with all this, you have to divide it by 1,000. All right, so the reason is the escape velocity, the way it's set up, the escape velocity is set up to be in meters per second. But the traditional thing to do with that, the usual thing that we do is we do the calculation in anyhow. It's often reported in kilometers per second. All right. So here we go. All right. Here, let me pause this and put the numbers in my calculator. So I put everything in my calculator. I paused it to do that just because it takes less time. All right, so there's the answer that I get. Sorry, I still have to take the square root. So I take the square root of that. There's the answer that I get. Remember, that answer's in meters per second. And then if I divide it by 1,000, here, let me move this so you can see the proper answer. All right, so if I divide it by 1,000, I'm going to get the same number that I have right here. So divided by 1,000 equals, all right, and so 19.6, right? That's exactly what I got. All right, so for the other one, let's see. I probably have enough time to do this one. All right, so 6.67. So I'm doing part B. 6.67 universal gravitational constant times 10 to the minus 11th times the mass of the planet, which is 4.9 times 10 to the 25th, divided by, don't forget, you have to square this, all right? So 16980, and you can write times 10 to the third, or just do 800, same thing. And don't forget, you got to square that and then hit equals. All right, and so you get 11.3. Right, we're rounding to one place past the decimal, so that's exactly what I got. Right, 11.3. Right, so that's number 16.